In this video, we take a look at section 3.4 about applications of determinants. Our learning objectives for section 3.4 are to find the adjoint of a matrix and use it to find the inverse of a matrix. Use Kramer's rule to solve a system of n linear equations and n unknowns. And use determinants to find area, volume, and the equation of lines and planes. So the last objective will be in the next video, where we'll see how we can use determinants to find the area, the volume, and equations of lines and planes. So we are going to see how to use the adjoint to calculate the inverse of a matrix, but we are also going to see that this is time-consuming and inefficient. So in practice, Gauss-Jordan elimination that we've seen in earlier sections is used for calculating the determinant for 3x3 matrices and larger. However, the adjoint is a vocabulary concept and a concept you may be expected to know in future classes, or you may need to know in a programming scenario. So recall from section 3.1 that the cofactor Cij of a matrix A is -1 to the I plus j times the determinant of the matrix obtained by deleting row I and column j of A. So cofactors are one-dimensionless matrices, and we saw that we can keep working down the cofactors in dimension until we end up at a 2x2 matrix where it's real easy to find the determinant. We also saw we could do row operations to make our cofactor calculations more simple for us, so that we get ones and zeros in a particular column we want to work with. So here's our matrix of cofactors. Something like C21 is a cofactor matrix corresponding with the second row and the first column, and C1n is the cofactor matrix corresponding with the first row and the nth column. So the adjoint matrix of A is the transpose of this matrix of cofactors. So notice cofactor C21 in the adjoint is now in the first row, second column. So the columns and row positions are reversed in the transpose here. Similarly, C1n that was in row 1, column n in the matrix of cofactors is now in row n, column 1. So it's a transpose. The diagonal stays the same, but the other entries reverse across the diagonal. Recall too, the cofactor signs alternate because -1 to the I plus j is going to be -1 when I plus j is odd, and a +1 when I plus j is even up there in the exponent. Theorem 3.10 tells us the inverse of a matrix is given by its adjoint multiplied by 1 over the determinant. So if A is an invertible matrix, then A inverse equals 1 over the determinant of A multiplied by the adjoint of A. So let's take a look at the proof here. So consider A multiplied by the adjoint of A. And so here's matrix A, and we've highlighted row I. And think about if we multiply that by column J in the adjoint matrix of A. So the ijth entry of the product is going to be the sum of each element of A multiplied by the corresponding cofactor matrix. So we've got AI1 multiplied by CJ1, AI2 multiplied by CJ2, added all the way up with AIN in the nth position, in the nth column, multiplied by CJN. All right. So if I equals j, this is just determinant A expanded by the cofactors in row I. If I and j are not equal, then this is the determinant of the matrix B, which is the same as A, except that row j is now replaced with row I. So let's take a visual of what that looks like. So here's matrix A, and we've got row j here in matrix A. Over here in matrix B, row j is replaced by row I, meaning we've got duplicate row i's here in matrix B. So let's take a look at matrix B here, multiplied by the adjoint matrix of A. So if we look at multiplying the ith row of B by the jth column of the adjoint matrix, then we have each AI element multiplied by each cofactor matrix Cj 1 through n. So the jth column of the cofactor matrix is unchanged because it doesn't depend on the j row of A or B. But since two rows of B are the same, the cofactor expansion for I and j different is going to be 0. So thus, matrix A multiplied by its adjoint matrix is going to be a matrix with the determinants on the diagonal and zeros everywhere else. So we can think about this as the determinant of A multiplied by I. Remember, the determinant of A is just some constant value, so it's like a constant multiplied by the identity matrix. All right, since A is invertible, the determinant of A is not 0. That's a typo there. And so we can write A multiplied by 1 over the determinant of A times the adjoint matrix of A equals the identity matrix. So then working backwards, if we want to get A by itself, we can say, oh, A inverse multiplied by the identity is just A inverse. So A inverse is 1 over determinant of A multiplied by the adjoint of A. Okay, so for 3 by 3 matrices and larger, this is going to be time consuming. So Gauss-Jordan elimination is much more efficient than the adjoint matrix method for finding the inverse of a matrix. However, for a 2 by 2 matrix, we have seen that this formula is pretty efficient and fast. So if our 2 by 2 matrix is AB in the first row and CB in the second row, then the adjoint for that matrix A is going to be D negative B in the first row and negative CA in the second row. So this is where our formula for A inverse for 2 by 2 matrix comes from. So it is 1 over AB minus BC, because that's our determinant, multiplied by this adjoint matrix of A, D negative B in the first row, negative CA in the second row. So we saw earlier in chapter 3 that it's pretty efficient, or actually back in chapter 2, it's pretty efficient to use this 2 by 2 formula for the inverse of a matrix. So it's okay to do that formula to find the inverse of a 2 by 2 matrix. For the inverse of a 3 by 3 matrix and higher, go ahead and use Gauss-Jordan elimination, or even simply, or your graphing calculator or other technology. Okay, so Kramer's rule is related. This takes determinants and uses the determinants to solve a system of n linear equations and n variables. So Kramer's rule was published in 1750. If that sounds like a long time ago, it was. So it's important for us to know how Kramer's rule works, but we know it's time consuming and not the way that we're going to be calculating in 2020. So we are going to use Gauss-Jordan elimination, or a computer system that's coded with Gauss-Jordan elimination to be time efficient. So in the case of n equations and n unknowns, the problem with Kramer's rule is that it requires computation of n plus 1 determinants. You have to calculate determinants 1 through n and determinant A. So you've got a little extra work. Imagine coding a computer where you're going to be working with a data set with hundreds of thousands and millions of values. It's going to be longer runtime for these extra calculations. All right, so Kramer's rule to solve n linear equations and n variables is time consuming and inefficient. In practice, Gaussian elimination is used to solve linear systems. However, we're studying this because Kramer's rule is a vocabulary concept you may be expected to know in a future class. You may see situations where you use it in applied fields in physics or chemistry or engineering. So if an n by n system, AX equals B, has a coefficient matrix A with a non-zero determinant not equal to 0, so determinant of A is not 0, then X1 is found by taking the determinant of what we call A1 divided by the determinant of A. So this determinant A1 is a matrix A, but the first column is replaced with the solution vector B. Similarly, X2 is found by taking the determinant of A2 divided by the determinant of A, where this A2 is matrix A, but the second column is replaced by the solution vector B. We can apply this for n solutions, so that Xn is found by taking the determinant of An divided by determinant of A, where An is the matrix A with the nth, or the last column, replaced by B, the solution vector. So let's look at the proof of Kramer's rule. So we're going to say X is X1 through Xn are solutions. Then X equals A inverse times B. We know that from chapter 2. That's how we can solve for our equation of X's. So A inverse is just 1 over determinant of A times the adjoint of A multiplied by B. So here's our adjoint matrix A. And here's matrix B over here. B is just a column. And so we think about, well, if we expand this out, then each row of cofactors here in the adjoint matrix gets multiplied by each B value. So for the ith row, we're going to have B1, C1I, plus B2, C2I, plus all the way through Bn, Cni, all multiplied by 1 over the determinant of A. But this right here is just the determinant of AI. So xi equals the determinant of AI, this expansion, divided by the determinant of A. So let's look at an example solving a system with Kramer's rule. So here's my system, and I'm going to take the coefficient values and put them in a matrix. Because this is a two equation to a known system, my matrix A is going to be a 2 by 2 matrix. 1, 2, 3, 4. And then my solution vector B is going to be 10 and 15 here in a column matrix. Okay, so on the bottom of our calculations for X and Y here, we have determinant of A. On the top here, in what we call matrix A1, the first column of A has been replaced by B. And to solve for Y, or what we call X2, if we call it this X1, we've got matrix A2, where the second column of A has been replaced by B. So we can go through calculating the determinant for these 2 by 2 systems. So for the determinant of A1, that's going to be 40 minus 30, or 10. And the determinant of A is 8 minus 6, or negative 2. So 10 divided by negative 2 gives us negative 5 here. Now for Y, or we could call these X1 and X2 if we didn't want to call them X and Y, we've got 15 minus 30 for the determinant of what we're calling A2, where the second row of, or the second column of A is replaced by B. So 15 minus 30 gives us the negative 15. The determinant of A is still negative 2. So our solution here is 15 over 2, or 7.5. So you can see Kramer's rule was not any faster than had we used the elimination method to solve this 2 by 2 system. So it's good to know Kramer's rule. It's important to know why it works, but we do most often rely on our usual calculus elimination methods. In the next video, we will take a look at how we can use determinants to solve areas, volumes, and find equations of lines and planes.